The ingenious design of the
holographic meatloaf.
Every year, near
4.000 pontos.
these cans are manufactured. That's about 15,000 per second. So many that we overlook the can's superb engineering. Let's start with why the can is shaped like it is. Why a cylinder? An engineer might like to make a spherical can. It has the smallest surface area for a given volume, and so it uses the least amount of material. And it also has no corners, and so no weak points, because the pressure in the can uniformly stresses the walls. But a sphere is not practical to manufacture, and of course, it'll... When packed as closely as possible, only 74% of the total volume is taken up by the...
雪花飘飘，北风萧萧。
The other 26% is void space, which goes unused when transporting the cans or in a store display. An engineer could solve this problem by making a cuboid-shaped can. It sits on a table, but it's uncomfortable to hold and while easier to manufacture than a sphere, these edges are weak points and require very thick walls. But the cuboid surpasses the sphere in packing efficiency. It has almost no wasted space, although at the sacrifice of using more surface area to contain the same volume as the sphere. So, to create a can, engineers use a cylinder, which has elements of both shapes. From the top, it's like a sphere, and from the side, it's like a cuboid. A cylinder has a maximum packing factor of about 91%, not as good as the cuboid, but better than the sphere. Most important of all, the cylinder can be rapidly manufactured. The can begins as this disc called a blank, punched from an aluminum sheet about 3/10 of a millimeter thick. The first step starts with a drawing die, on which sits the blank and then a blank holder that rests on top. We'll look at a slice of the die so we can see what's happening. A cylindrical punch presses down on the die, forming the blank into a cup. This process is called drawing. This cup is about 88 millimeters in diameter, larger than the final can, so it's redrawn. That process starts with this wide cup and uses another cylindrical punch and a redrawing die. The punch presses the cup through the redrawing die and transforms it into a cup with a narrower diameter, which is a bit taller. This redrawn cup is now the final diameter of the can, 65 millimeters, but it's not yet tall enough. A punch pushes this redrawn cup through an ironing ring. The cup stays the same diameter as it becomes taller and the walls thinner. If we watch this process again up close, you see the initial thick wall and then the thinner wall after it's ironed. Ironing occurs in 3 stages, each progressively making the walls thinner and the can taller. After the cup is ironed, the dome on the bottom is formed. This requires a convex doming tool and a punch with a matching concave indentation. As the punch presses the cup downward into the doming tool, the cup bottom then deforms into a dome. That dome reduces the amount of metal needed to manufacture the can. The dome bottom uses less material than if the bottom were flat. A dome is an arch revolved around its center. The curvature of the arch distributes some of the vertical load into horizontal forces, allowing a dome to withstand greater pressure than a flat beam. On the dome, you might notice 2 large numbers. These debossed numbers are engraved on the doming tool. The first number signifies the production line in the factory, and the second number signifies
life, huh?
The body maker is the machine that performs the redrawing, ironing, and doming processes. These numbers help troubleshoot production problems in the factory. In that factory, the manufacturing of a can takes place at a tremendous rate. These last 3 steps, redrawing, ironing, and doming, all happen in one continuous stream in only a second per second. The punch moves at a maximum velocity of 11 meters per second and experiences a maximum acceleration of 40 kilometers. This process runs continuously for 6 and uneven. These irregularities occur during the forming. To get a nice, even edge, about 6 millimeters with an even top, the can can now be sealed. But before that sealing occurs, a colorful design is printed on the outside. The term of art in the industry is The inside also gets a treatment. A spray-coated epoxy lacquer separates the can's contents from its aluminum walls. This prevents the drink from acquiring a metallic taste and also keeps acids in the beverage from dissolving the aluminum. The next step forms the can's neck, the part of the can body that tapers inward. This necking requires 11 stages. The forming starts with the top is brought slightly inward, and then this is repeated further up the can wall until the final diameter is reached. The change in neck size at each stage is so subtle that you can barely tell a difference between one stage and the next. Each one of these stages works by inserting an inner die into the can body, then pushing an outer die, called the necking sleeve, around the outside. The necking sleeve retracts, the inner die retracts, and the can moves to the next stage. The necking is drawn out over many different stages to prevent wrinkling or pleating of the thin aluminum. Since the 1960s, the diameter of the can end has become smaller by 6 millimeters, from 60 millimeters to 54 millimeters today. This seems a tiny amount, but the aluminum can industry produces over 100 billion cans a year, so that 6 millimeter reduction saves at least 90 million kilograms of aluminum annually. That amount would form a solid cube of aluminum 32 meters on a side. Compare that to a 787 Dreamliner with a 60-meter wingspan. Now, after the neck has been formed, the top is flanged. That is, it flares out slightly and allows the end to be secured to the body, which brings us to the next brilliant design feature, the double seam. On older steel cans, manufacturers welded or soldered on the ends. This often contaminated the can's contents. In contrast, today's cans use a hygienic double seam, which can also be made faster. This can is cut in half so you can see the cross-section of the double seam. To create this seam, a machine uses two basic operations.
Repair the truck. Okay, there it goes. We're in the death wobble right now. We're trying to keep the truck on the road. You cannot operate the brakes at this time. Do not try to brake during a Ford death wobble. Just let the truck decelerate. Eventually the front end will try to, you can see that if I allow the wheel to stop, it's an extremely violent.
While the operations themselves are simple, they require
Pickle Rick!
Parts misaligned by a small fraction of a millimeter cause the seam to fail. In addition to the clamping of the end and can body, a sealing compound ensures that no gas escapes through the double seam. The compound is applied as
天地一片
then hardens to form.
苍茫。
The end, attached immediately after the can is filled, traps gases inside the can to create pressures of about 30 psi or 2 times atmospheric pressure. In soda, carbon dioxide produces the pressure. In non-carbonated drinks like juices, nitrogen is added. So why is a beverage can pressurized?
4.000